Hi everyone, welcome back to the channel. In today's video, we're going to be going over potential energy and what that really means. We did a little bit of it informally in the last video, but in today's video, I want to make sure we understand what it really means. And so remember that energy is equal to, it just basically means the ability to do work, right? And we kind of went over this in the last video as to how energy and work are related. So if you need a refresher, you can go there. But just to make it super easy for you, you need energy to do work, right? Just like going to work every day, you need energy to go to school or to go do work, right? In the physics sense, you need energy to do work. You need energy to cause something to move, right? And so what you get to is the idea that work is equal to the change in energy, right? And that's why we set this sentence right here, the ability to do work. So what is this concept of potential energy, right? To make this easy, let's start with gravitational potential energy. What I want you to remember, what I want you to look at, is you have this object right here in red with some mass, right? And so the only force acting on it is mg, which is the force of gravity along the entire distance, right? And so what you can see is that at point A, right here, work is equal to 0 because nothing's happening. The object is just sitting there, right? And so what is energy equal to? So energy is equal to work, right? And so energy is equal to delta work, right? So keep this in mind. Energy is equal to the change in work, right? And there's no work being done here, right? But we know for sure that work is being done every single time / distance after point A. And so the question becomes, is energy equal to 0 at point A? You can say, yeah, because no work is done, there's had to be no energy, right? But if you go back to the idea of basically energy cannot be created or destroyed, right? That would disprove that point. Because if you said that energy is equal to 0 at this point, right? What that means is there was no energy and then the object got energy right after point A, which would mean that energy was somehow created or destroyed in that system, right? And so what you can say is this is not possible, right? And so there is energy at point A, but it's not doing anything, right? It's just stored energy. And when we have this kind of stored energy, we can say, okay, if the only force acting is gravity, well, we can call it a potential energy because it's stored and hasn't done anything. And we can add the two together because gravity is the force acting. We can say it's gravitational potential energy. And so the equation for that, we'll get into right now, the math behind why this makes sense. Remember, total mechanical energy of a system is equal to its kinetic energy plus its potential energy. And the work of a mechanical system is equal to the change in mechanical energy, which again is equal to the change in kinetic energy plus the change in potential energy. And so if you go back to the idea of what work is equal to force times distance cosine of theta, right? And so what is work being done for this object, right? Remember, if work is equal to force times distance cosine of theta, what is the force? The force in this case is gravity, which we call mg, right? And then the distance is equal to the displacement in this case, which is h, which we got right over here, right? And so then when you combine these two, you're missing one thing. What is the theta, right? Now, to think about what the theta is in this case, what the angle is between motion and the force, you have to think about what's happening in the situation. You have this object right here, and you have gravity going straight down. And so what you can see is that they're both pointing in the same direction. Motion goes down, gravity goes down. So there is no angle between the two. It's just 0, right? Because they both motion goes down, and so does gravity. And so if their two arrows are like this, there's no angle difference between the two. And so theta is equal to 0. What is cosine of 0? It's just 1, right? And so when you write it out, you just get work done by gravity is equal to mgh. And then, remember, we talked about this earlier. If work done by gravity is equal to mgh, and we know the change in energy, remember, work done by gravity is equal to then the change in kinetic energy plus potential energy, right? And so we said the work being done was equal to 0. And so if that's the case, delta KE, the change in kinetic energy, is equal to negative potential energy, and vice versa. Change in potential energy is equal to negative change in kinetic energy. Remember, when you see this, right, this relationship just tells you the negative sign doesn't mean it's negative or positive. It just means they're always opposite to each other, right? If you have a lot of kinetic energy, you have very little potential energy, and vice versa. It just means they're opposite. And so when you put this all together, we say work done by gravity is equal to the change in potential energy, and that would be equal to what we had above, mg delta h. And so you can say potential energy is just equal to mgh. And then at the same time, it's also equal to the change in kinetic energy. And so the kinetic energy done by gravity is also equal to 1/2 mv squared. Now that you understand a little bit more about gravitational potential energy, you might be a little bit confused as to where I got this U from, right? Why not PE or something, right? And so potential energy has various notations, right? You can have it as UE, U, UG, US, PE, PES, PEG. And I've written out exactly what each of them means over here so that you can take a look at it. But generally, you can have it as any of these notations, as long as you don't put S for gravitational potential energy, you'll be okay, right? G represents the gravitational, and S represents the spring potential energy, which we'll get into in just a moment. And so, remember, work done by a spring is equal to 1/2 kx squared, which we proved above using Hooke's law, right? And so the change in energy of a mechanical system is equal to the work done by a spring, right? Because work is equal to change in energy. And so we go through the same derivation, right? And we end up with the same thing. And so what you get is if work by a spring is equal to 1/2 kx squared, and that is equal to the change in potential spring energy, you get this equation right here that tells you that the potential energy of a spring is equal to 1/2 kx squared. And that's, again, the same idea as gravitational potential energy. We'll look at the spring to make it easier for you. If you take a look at this spring, right, this has no work being done. This has work being done, right? And so this is the same spring either being stretched or compressed. And so what you can see is, again, if energy over here is equal to 0, then it's not possible because the conservation of energy says that the energy is conserved. And so what you see is that at this point, there had to be energy when the spring was at its normal position, right? So that when you pull it, you do work on the object, and if work here is equal to 0 and work over here is equal to some number, right? And we talked about this earlier. Is energy equal to 0 then? No, because energy is equal to the change in work. And so if work is changing between 0 and a number, then energy has to be some number even at this initial point. And we'll call that spring potential energy in this case.